Have you ever looked up at the night sky and wondered about the power behind those stars? The vastness above us is filled with mysteries, each star a distant sun, burning with unimaginable energy. For centuries humans have gazed upward, searching for answers about our place in the cosmos and the forces that shape our universe. That same cosmic energy is hidden in the atom, the building block of everything. Atoms are the tiny engines of the universe, containing within them the same forces that light up the stars. Every object, every living thing is made from these invisible particles, each one a miniature universe in itself. Uranium, forged in ancient supernovas, lay dormant in Earth's crust for eons, waiting for discovery. This element, created in the heart of dying stars, traveled across space and time before settling deep within our planet. Its journey is a story billions of years in the making. Unlike gold or iron, uranium is unstable, radioactive, its nucleus packed with restless energy. It glows faintly in the dark, a silent reminder of the immense power locked inside. Handling uranium requires caution, for its energy is both a gift and a danger. When a uranium atom is split in a process called nuclear fission, it releases an astonishing amount of energy, far beyond any chemical reaction. This process transforms a tiny fragment of matter into pure energy, echoing the forces that power the stars themselves. This split also releases neutrons, triggering a chain reaction, a cascade of splitting atoms that can power cities or unleash destruction. The chain reaction is both a marvel of science and a sobering reminder of the responsibility that comes with such power. The story of unlocking this power begins deep within our planet, with a single extraordinary element. From the heart of the Earth to the heart of the atom, uranium connects us to the stars, reminding us that the universe's greatest forces can be found in the smallest places. Our journey begins deep beneath the Earth's surface, where miners work tirelessly to extract uranium ore. This ore appears as dull, dark rock, hidden among layers of stone and earth, and it takes both skill and determination to bring it to the surface. The process is challenging and often dangerous, requiring specialized equipment and strict safety measures to protect the workers. Once above ground, the ore is transported in massive quantities. Each load contains only a tiny fraction of uranium, so enormous amounts must be mined and moved to make the process worthwhile. Heavy machinery and conveyor belts help move these vast piles to the next stage. At the milling facility, the ore is crushed into fine particles. Then, it's mixed with acid in large tanks, a process called leaching. The acid dissolves the uranium, much like tea leaves infuse their flavor into hot water, separating it from the surrounding rock. The resulting uranium-rich solution is carefully purified to remove impurities. After purification, it's dried, leaving behind a concentrated bright yellow powder known as yellow cake. This powder is the first major milestone in uranium processing. Yellow cake is actually uranium oxide, a concentrated form that's stable and easy to transport. It's packed into secure containers, ready for the next phase of its journey. However, most of this yellow cake is made up of uranium-238, which is stable and cannot sustain the chain reactions needed for nuclear power or weapons. It's not the part we're after. The true prize is uranium-235, a rare isotope that makes up less than 1% of natural uranium. This isotope is the key ingredient for nuclear reactors and atomic bombs, but it's incredibly scarce. The next challenge is perhaps the most complex, separating and concentrating this elusive uranium-235 from the much more common uranium-238. This step, called enrichment, is essential for unlocking uranium's true potential. To use uranium for reactors or weapons, we must enrich it. Increase the percentage of U-235. U-235 and U-238 are nearly identical, differing only slightly in mass. The solution? Convert yellow cake to uranium hexafluoride gas, UF6, which can be separated by exploiting that tiny mass difference. In gas form, lighter U-235 molecules move just a bit faster than U-238. This subtle difference is the key to enrichment. The entire enrichment industry is built on this minuscule fact of physics. Humanity's quest for power led to a machine that spins at incredible speeds, the centrifuge. The gas centrifuge is the heart of uranium enrichment. Picture a tall, thin cylinder spinning at supersonic speeds. UF6 gas is fed inside. Heavier U-238 molecules are flung outward, while lighter U-235 molecules stay closer to the center. The separation is tiny, so thousands of centrifuges are linked in a cascade, each step enriching the gas a bit more. For nuclear power, uranium is enriched to 35% U-235, low-enriched uranium. For weapons, enrichment continues to 90% or more, highly enriched uranium. The same technology can produce both. The difference is how long uranium stays in the cascade. This process is tightly controlled and monitored worldwide. Most enriched uranium fuels nuclear power plants, generating electricity for millions of homes and businesses around the world. These plants are a cornerstone of modern infrastructure, quietly providing the energy that powers our daily lives, from lighting our cities to running our industries. Inside the heart of these reactors, tiny uranium pellets are carefully stacked into long rods. These rods are then bundled together to form fuel assemblies which are precisely arranged to sustain a controlled chain reaction. This process is monitored by skilled technicians to ensure safety and efficiency at every step. The heat released from splitting uranium atoms is immense. It boils water to create high-pressure steam, which spins massive turbines. This mechanical energy is then converted into electricity, flowing out to power entire communities, all without the air pollution of fossil fuels. Remarkably, a single uranium fuel pellet smaller than a fingertip can produce as much energy as a ton of coal or several barrels of oil. And it does so without releasing greenhouse gases, making it a powerful tool in the quest for cleaner energy. Nuclear power is not only reliable and efficient, but also one of the lowest carbon energy sources available. It plays a vital role in the fight against climate change, helping nations reduce their carbon footprints while meeting growing energy demands. Beyond electricity, nuclear reactors produce isotopes that save lives every day in hospitals, diagnosing and treating diseases. They also power spacecraft, enabling humanity to explore distant planets and the far reaches of our solar system. The atom's energy is a remarkable gift, clean, powerful, and brimming with potential for innovation. It offers hope for a sustainable future, if we use it wisely. But this gift comes with great responsibility. Safe operation, careful waste management, and constant vigilance are essential to ensure that nuclear power remains a force for good in our world. The same process that powers cities can also destroy them. Highly enriched uranium enables uncontrolled chain reactions, the principle behind atomic bombs. Two subcritical masses are joined, triggering a devastating explosion. Hiroshima and Nagasaki remind us of this terrible potential. That's why uranium enrichment is strictly regulated, with international agencies monitoring every step. The atom offers both hope and danger, a clean energy future or catastrophic destruction. Understanding this science empowers us to shape our world's future. Is the promise of nuclear energy worth the risk? Let us know your thoughts and what mysteries you want to explore next.